Okay, hopefully the last little bit before your test. We're going to talk about the applications of thermodynamics, entropy, Gibbs free energy, and some voltage. Okay, entropy is a measure of a randomness and disorder of a system. The greater the disorder, the greater the entropy. Zero entropy is defined as a solid crystal at 0 degrees Kelvin. 0 degrees Kelvin has never been reached experimentally. Therefore, all entropy we discuss will be a positive number. Standard entropies are calculated at 25 degrees Celsius. However, we will almost always use Kelvin. In fact, not almost always, we will always use Kelvin for these calculations. So delta S, the change in S, the change in randomness is equal to the randomness of the products minus the entropy of the reactants. So Gibbs free energy is G. It is a measure of whether or not the process will proceed without adding outside energy. A process that would complete without the addition of outside energy is thermodynamically favored, also known as being spontaneous. A process that requires the outside energy to complete is considered thermodynamically unfavored, also sometimes called non-spontaneous. The free energy change is the change in Gibbs free energy of the products minus those of the reactants. If delta G is negative, the reaction is thermodynamically favored. If the G is positive, the reaction is thermodynamically unfavored. If delta G is 0, then the reaction is in equilibrium. So if it's negative, it's favored. If it's positive, it's unfavored. And if it's 0, it is in equilibrium. Okay, so we have the enthalpy and we have the entropy. We can work these problems out. So T is the absolute temperature. Again, we're doing Kelvin. All these energy problems seem to be using Kelvin. When working these equations, make sure your units match up. And the one that we're going to do, you'll see that our delta H is kilojoules per mole and our delta S is joules per mole. So we need to convert this, the 135 joules per mole, and you can go either way. Most people go ahead and convert to, or most seem to convert to kilojoules, and that seems to be the way the test normally converts. So this would be negative 0.135 kilojoules per mole. Okay, so is it thermodynamically favorable at 25 degrees Celsius? So when we look at our formula again, it was delta G is equal to delta H minus temperature times delta S. And our temperature is at 25. We need to convert that to Kelvin. So 273 plus 25 is 298. So I list my variables, delta G, delta H, T, and delta S. Delta G is what we're looking for. Our delta H is negative 41 kilojoules per mole. Our temperature is 298 degrees Kelvin. And our delta S is negative 0.135 135 kilojoules per mole. So now we just need to plug this into our equation. So delta G, I'm going to change our color. Delta G is equal to delta H, which was negative 41 kilojoules per mole, minus our temperature, which was 298 degrees Kelvin, and our times our delta S, which was negative 0.135 kilojoules per mole. And when we put this into a calculator, we get that that delta G is equal to negative 0.97 kilojoules per mole. So it is negative, therefore it is favored. Okay. Okay, so same equation, we're looking for different information. And it says at what temperature would the reaction no longer be thermodynamically favored? So remember, at 0 or less than 0, it's no longer thermodynamically favored. So we can set our equation is delta G is equal to delta H minus our temperature in Kelvin times delta S. Okay, so at this point we're looking for our temperature. So let's list our variables. We have delta G, delta H, T, and delta S. And in this case, our temperature is what we're looking for. Our delta G is going to be 0, because anything at 0 and lower, it's going to no longer be favored. So delta H is negative 41 kilojoules per mole, and our delta S is negative 135 joules per mole. And again, we need to convert that to make sure it's kilojoules. So it's equal to negative 0.135 kilojoules per mole. So we plug this into we're looking for T. Okay, we're looking for T, so rearranging our equation, we will get delta G plus T delta S is equal to delta H. We need to move the G over, so it's going to be T delta S is equal to delta H minus delta G, and then divide both sides by delta S. So our T is going to equal delta H minus delta G over delta S. So delta H was negative negative 41 minus 0 divided by negative 0.135. And this is going to equal 305 Kelvin. And remember, I am the worst. This should be kilojoules per mole. That would be kilojoules per mole. And this is kilojoules per mole. Okay, this is just a chart. If delta H is negative, if the delta S is positive, and the temperature is low, then basically if the delta H is always positive or is always negative and our delta S is always positive, then it's always favored, whether the temperature is high or low. If our temperature is high and our delta S is low or negative, then in a low temp, then neither way is it favored. So a positive delta H and a negative delta S is never favored. A positive delta H and a positive delta S, is only favored at high temperatures. A negative delta H and a negative delta S is only favored at low temperatures. Okay, so the G and the phase change. Okay, so phase change is not a chemical reaction. So delta G at phase change is 0. So acetone is a liquid at room temperature with a delta H at vaporization of 29.1 kilojoules per mole, and a delta S vaporization is equal to 88, again, joules per mole as opposed to kilojoules per mole. What is the boiling point of acetone? Okay, so our formula, again, is delta G is equal to delta H, and in this case at vaporization, minus T delta S at vaporization. So we said delta G is going to be 0. Delta H is going to be 29.1 kilojoules per mole. Delta S is 88.4 joules per mole, which is equal to 0.0884 kilojoules per mole. And T is our unknown. So we plug this into the equation. We have 0 is equal to 29.1 kilojoules per mole minus T, and delta S, which is 0.0884 kilojoules per moles Kelvin. We have T times 0.0884 kilojoules per mole equal times Kelvin is equal to 29.1 kilojoules per mole. Divide both sides by 0.0884. And our answer is going to be 329 degrees Kelvin. Okay, so the amount of Gibbs free energy in any given reaction can also be calculated if you know the equilibrium constant expression for the reaction. So if delta G is going to equal R times temperature, again, temperature is done in Kelvin. It's done in Kelvin, and inverse K, whereas R is the gas constant, 8.31, and K is the equilibrium constant. Reduction potentials. Every half reaction has an electric potential or voltage associated with it. They will always give you the standard half reactions for reduction potentials. So if it's oxidation, you have to flip the equation and change the sign. So the reduction potential for zinc plus 2 will be given to you as negative 0.76. However, if it was asking for the oxidation potential for zinc, we flip the equation. Reduction means we're gaining electrons, so our oxidation number is decreasing. So we're going from a +2 to 0. So it's decreasing, so it's being reduced, so that's a reduction. Oxidation potential, zinc, if we're going the other direction, zinc, now our number is increasing. As we lose electrons, then our oxidation number increases. And so this is oxidation, and we just flip the equation, and it is the opposite charge. The larger the potential for a half reaction, the more likely it is to occur. So if you look at both of these, and again, this should be F2. Then iron being reduced has a plus 2.87. Lithium being oxidized has a plus 305. The more positive, the more likely it is to occur. So this one, the lithium, being oxidized is more likely to occur. Okay, so if we look at this, and in redox reactions, something's being reduced and something's being oxidized. Something is gaining electrons and something is losing electrons. So the oxidation is losing the electrons. So zinc plus 2 electrons has a voltage charge of 0.076. The silver gaining electrons has a reduction potential of 0.8. So to find out the potential for the overall equation, we add the two numbers together. So this would be 0.76 plus volts plus 0.08 volts. I'm sorry, 0.8 volts is going to equal 1.56 volts. So when you're looking for the overall, then you just add the two numbers together. Okay, so when we're talking about different voltage cells, and the first type is a galvanic cell. And the one thing you need to know about all these cells that we're going to talk about is anox red cat. The anode is the site of oxidation. The cathode is the site of reduction. So on the anode, the substance is losing electrons, and on the cathode, it's gaining electrons. And the electrons that are released on the oxidation reaction, they pass through a wire to the chamber where they're being consumed by the reduction reaction. Electrolytic cells, again, anox red cat is still the same. That's true of all these cells. The outside source of the voltage used to force the unfavored reaction. These are usually done in aqueous solutions. Okay, so if we look at these two, a solution of nickel chloride, two things are happening. The nickels and the chlorine are breaking apart and becoming associated with the water. So the first thing we need to do is compare the reduction potential of the cation. Remember, cation is C, a positive ion, with the reduction potential of water. The most positive is the one that will occur. So if we look at these two, this is more positive. Negative 0.25 is closer to the zero than negative 0.8. So this is favored. When we look at the oxidation potential, and remember, it's always going to give you the reduction potential. So you'll have to rearrange the equipment and flip it, rearrange the equation and flip it, and that's already been done here. So the chlorine has a negative 0.136, and the water has a negative 1.24. However, the water is actually being oxidized. So the nickel is being reduced, but the water is being oxidized. And then you would add those two numbers to get the E for the entire equation. So negative 0.25 volts plus negative 1.24 volts is equal to negative 1.49 volts. Okay, so that looks like it was mostly it. The only other thing that was left on here had to do with electroplating. and calculating the number of moles. And I may just, I will do this one maybe at the end of class. But so that's it for today. Thank you. Y'all have a great day.